Hi guys. Okay, now we're going to talk about what I think is an extremely interesting subject, and that's the temporal aspects of the effect and concentration relationship. So most models assume that with time, as concentration declines, so does your effect. So when you think about our model, as concentration increases, our effect increases. As concentration falls, our effect falls with time. But it's not always true, because the response may lag behind the concentration. Therefore, would not parallel plasma concentrations. The response may also decrease with time at the same concentration. So response may lag behind, or it may decrease as time goes on. So that's what we're going to talk about now. Okay. So let's say case number one. Here's case number one. Our effect has a linear relationship with concentration. So what that means, right, is that as concentration increases, our effect increases in a linear fashion. That means we start at concentration of 0, and when our concentration is 0, our effect is 0, and we have this linear relationship, and this slope is going to be Emax over C50 for a linear relationship. Okay, response and plasma concentrations were simulated during and after a 1-hour infusion. So we gave a 1-hour infusion. So the drug was given over 1 hour. So we can see here the concentration is here. So we can see the concentration increases over that hour infusion. This should go to 0, and then it's going to start to decline after that 1-hour infusion. It declines in a log linear way. See, this is a log, right? So it's both our concentration and our effect in percent. So you can see that this declines in a log linear fashion. Note that the time course and responsive concentrations parallel each other. Well, I didn't even get to the response, did I? So if we plot our response, so let's say our response is, let's say that we have an increase in heart rate. So our heart rate increased to its maximal effect at 100, and then it started to fall just as the concentration fell. So you can see that the concentration and effect fall together in parallel. So concentration goes up, effect goes up, concentration starts to fall, effect starts to fall. So concentration goes up, effect goes up. As concentration falls, effect falls. It's a perfect linear relationship. This is what I think most people think happens all the time, but that is not, in fact, true. So here's case number 2, where we lag the concentration. Whoopsie. So we give a single IV dose is given in this case over 30 minutes, just like before, or was it an hour? I don't remember. But let's say this is concentration, log concentration. This is time. We give 30 minutes, and then we let the drug fall down, and we also measure effect. So let's say this is also effect. We have to see what happens with effect, just like that other graph in the last slide. Here we're going to have a lag. Okay, so notice these are not necessarily parallel. What this shows us is that as our concentration, so we have a Tmax at 30 minutes because we're giving this is our concentration in blue again. As we increase our concentration, because it's given over a half hour, and then the infusion stops and the drug starts to decline. This is linear here, right? So this is declining in probably a log linear fashion. So we can see here that our Tmax is at 30 minutes, okay? And then what's happening with our effect? Our effect is also increasing, isn't it, as the concentration increases. But now as the concentration falls, our effect continues to rise, doesn't it? Our concentration is still falling and our concentration is still rising. So here's where we get to our maximum effect, and it's certainly not at our maximum concentration, is it? Our concentration has already fallen to about 0.3 here, right? So we can see that the maximal effect lags our maximal concentration, doesn't it? So our Tmax for our concentration is at 30 minutes here, whereas our Emax for the effect is, well, it says 4.5 hours. We've got, I'm looking at about 5, but I mean, this was modeled, so I'm sure 4.5 hours is right. So we have a lag because the maximum concentration occurred at 30 minutes and the maximum effect at 4 hours later. So you can see that there's a lag here. So the intensity of the response increases while concentration decreases between 1/2 and 4.5 hours. So while the concentration fell for 4 more hours, the effect continued to rise. This is called a lag. You should probably understand the name of that. There's a lag between the concentration and the effect. So what do we do with this data? Because this is confusing, isn't it? If we take this data, we see at time 0, these are all, whoopsie. We see at time 0 that these are all zeros, right? So at time 0, the concentration is 0 and the effect is 0. At 20 minutes, so this is as our concentration increases, because remember it's given for a half an hour. So at 20 minutes in, the concentration is 0.328 and our effect is 0.34. This is all just taken from that last graph, so maybe we can go back there and see it. At time 0.33, so it's somewhere in here. So our concentration and effect, whoopsie. Our concentration and effect are right in here, right? But then if we go to 4.5 hours, the concentration is literally the same because now the concentration is falling. So the concentration is, let's say it's, I don't know if I'm going to get this exactly right, but I'll try. So our concentration is the same both here and here, right? But our effect is here. So our effect is like 3.5 or 0.35 here or so. But our concentration here, our effect is 0.85 or so at the same concentration. So at the same concentration, we have very different effects, don't we? So this is very confusing. So we see that data here. We see that at same concentration, but earlier in time, we have an effect of about a 0.34, 34%, but at 4.5 hours, we have an effect of 0.87. So what do we tell the FDA? So do we say when the concentration is 0.328 that they have an effect of 34% or of 0.87? So if response corresponds to 0.8 units, what concentration would you say this drug exerts an effect response? Would you say 0.327? I don't think so. Because it also could, depending on the time, it could also only would be less than what was needed for a response. So when this happens, it's called a hysteresis, which is one of my favorite words. Hysteresis. It's hysterical. Hysteresis. Crazy hysteresis. All right, so what is a hysteresis? Well, when you plot the E versus C, so as we have been, right, our concentration versus effect relationship, you need to plot it as per time, okay? So here we would have as our concentration goes up, our effect goes up, right? And then as so we're going to say this is time, okay? Let's say this is the top concentration we achieve. And then let's say our concentration starts to fall, and we have to plot that. I'm going to make it a different color. And then we have to plot that as well per time. Okay? So we plot these sequentially and in the order in which they were collected. And you need to connect the lines. If they are not superimposable, then you have a hysteresis. This is not a hysteresis. This is all on the same line. Now let me show you a hysteresis. Is everything okay?
I don't know when to be done.
Is it bubbling on the top? Okay, take it out. That's good. Sorry, we're making dinner here. Okay, let me draw that again. Concentration effect. So now let's say we have what we just showed. We showed that as the concentration increases, the effect increases. But as the concentration starts to fall, the effect actually starts to rise. And then eventually the concentration falls again. So these are not superimposable, are they? And this forms a loop. You can see the loop, I'm sure. And this is called a hysteresis. If it forms a loop, it's a hysteresis. Okay, so this would be a hysteresis showing a lag, right? I'm going to talk you through that one more time. Okay, the concentration increases, the effect increases, the concentration is still increasing, the effect is still increasing. Now the concentration starts to fall, but we still have an increase in effect, and we're starting to fall, and still the effect is increasing. Now the effect starts to fall as the concentration falls. Okay, so there's a lag. As the concentration is starting to fall, the effect is still increasing. This is a lag. One thing I also want you to notice is the direction of this loop that is formed. It's counterclockwise. What if we had the opposite situation? I'll just erase all. And this time, as our concentration increases, our effect increases, our concentration is still increasing, but our effect starts to fall. We're still increasing in concentration, but our effect is falling. And eventually, again, our effect falls even as our concentration falls. This is also a hysteresis. And this is usually due to tolerance, and it is a clockwise. See how it moves clockwise? It's a clockwise, and it's usually due to tolerance. Our concentration increases, but our effect starts to decrease, right? That's a clockwise hysteresis. I think I've skipped ahead, but it gives you an overview of what we're going to talk about in the next few slides. Okay, so I plotted this data. Here's our all our time data, the concentration data, and our effect data when we're going from 0 to 1. This is a percentage. If you think about it, 0% to 100% of Emax here of our effect, okay? So if I plot all of these data that we collected on one graph with time here and concentration and effect plotted on the y-axis, what would this look like? So I did that, and it looks like this. So as the concentration increases, as our concentration increases, our effect is increasing. Now our concentration starts to fall, but our effect is still rising. So this is a lag, isn't it? This is a lag, and you can see that it's counterclockwise. So at any particular concentration, we have two effects, don't we? Oh, that's so confusing. Yes, it is, but fascinating, right? So concentration is not the only thing that dictates the effect. It's concentration and time, isn't it? So what the heck do we do with this? We have to understand it in order to be able to use it. Oopsie. Now I'm going to quickly talk about the three models or mechanisms of a counterclockwise hysteresis, where we have this counterclockwise hysteresis is when we have a lag. So it's when, as our concentration increases, our effect increases, our concentration still increases, but our concentration starts to fall and our effect still goes up, and then eventually it falls. There's three different things I want you to know that could cause a counterclockwise hysteresis. One is an active metabolite. So if an active metabolite, if the actual effect is based on a metabolite, the concentration of the parent drug isn't going to be that correlated with the effect, right? It's going to take a while. The parent drug has to build up in order to make metabolite if the metabolite's actually the active form. So now more metabolite is being made, but so it's catching up, and the effect starts to increase even though the concentration of the parent drug is falling. So the first one I want you to know is active metabolite. An example for this is that morphine is, when we give morphine, it's actually the metabolite that gives the pain relief. So there's a lag. Another mechanism for this is when there's an effect site. So an effect site is where the drug has to move maybe from the blood into maybe the heart tissue or the muscle, or somewhere where the drug actually has to move from the blood to an organ to have the effect. Remember, this concentration is measuring blood concentration. So if it has to get to a specific site, then there's going to be a lag, isn't there? Because we're not, again, in both of these cases, we're not measuring the right thing. We're measuring parent drug when we should be measuring metabolite. Here we're measuring blood when we should be measuring the tissue where the drug needs to be. In neither case are we going to be able to do either of those easily. That's why there's a lag. The third possibility is turnover, which is a super interesting concept. With turnover, warfarin's probably the best example of this, and I'll use warfarin to describe it. I'm going to erase all of this. So when we give warfarin, the way it works is by inhibiting the vitamin K dependent clotting factors. So it's a anticoagulant. So it stops your body from making clots, right? So it does it by inhibiting the vitamin K dependent clotting factors. So in order for it to work, it has to stop the manufacturing of these vitamin K dependent clotting factors. So as our concentration of warfarin increases, it's shutting down the making of those vitamin K dependent clotting factors. So is it going to be a direct effect? No, because what it really depends on is how long it takes to get rid of the current vitamin K dependent clotting factors that are already in the body. So you've got a certain level of vitamin K dependent clotting factors, let's say it's here, right? And you need to wait for those to be cleared from the body, because you've stopped the manufacturing. So you've got to wait till this level drops, right? So it's really all about the half-life of those vitamin K dependent clotting factors. And the half-life of the longest vitamin K dependent clotting factor is about 72 hours or 3 days. So it takes 3 days to start getting rid of the vitamin K dependent clotting factors that are around, so that inhibition of making stopping the making of those clotting factors can kick in. So there's like a 3-day lag, isn't there, because of this turnover model. Oopsie. Okay, sorry. So this shows you the effect model. So we have drug coming into the plasma, right? And drug being eliminated from the plasma. It can move to a compartment here. It can also move to wherever the tissue whatever tissue it needs to be in. So let's say, is it the heart for digoxin to work? Is it muscle for I can't think of anything, but where does the drug have to go to have its effect? So there will be a lag because the drug has to move from the plasma into that particular tissue compartment. So that's the effect compartment, like digoxin or other drugs that have to be in a particular effect site. This one shows digoxin data, okay? So what you see here is the plasma digoxin concentration and the number of hours. So you can see here this dark dot is the concentration falling, right, over time after you give the drug. What's going on here is the left ventricular ejection time, which we want to prolong with digoxin. So what's going to happen? Even though the concentration is the highest here, we see a delay, don't we? And the effect of increasing the ejection time takes a while, doesn't it? So it's actually working, it's increasing as the concentration is decreasing, because it takes a while for the drug to get into the heart. Okay, Okay. And then what we see on this, sorry, I just lost my drawing thing. What we see in this graph is as the plasma concentration increases, we see the left ventricular ejection fraction decrease. It's really another way of showing that same data.